quickly revise what we had done last time. We had started discussing this problem of gambler's ruin. And what was the problem? So, how it was defined was that there are two people who are playing a game of betting some capital, and at each step they are betting a capital, let's say by an amount one. And the game is the following, that they start with an initial total capital between them, which is capital N. And then, so let us say A starts with 20 and B starts with 80. And then they, like I said, they toss a coin or do something. And basically there is some probability with which A wins the game. A wins a particular event, and B wins the particular event. And the game finishes whenever whatever be the starting capital of A, if either the total capital of A becomes zero, that means he keeps on betting this money, and finally every time, so let's say he bets the money and then loses one rupee and so on. So the game goes on until A has zero money, that means he's left with no money. That is one possibility. Or the other possibility is that A wins all the money. That means between A and B, if they had 100 rupees, although A started with 20 and he kept on winning, and finally if he becomes 100 and B has no money, then the game finishes. And the question we are interested in asking is, given a certain amount of initial money that A started off with, given the probabilities of the individual events which are given by this P and Q, that means for each of the small event, the probability of A winning and Q is the probability of A losing. What is the probability that the A wins the game? So that was the question we were interested in. And then last time what I argued was that you have this recursion relation which would be satisfied by P of I, if you want to like put subscript A. And this relation is telling you what it is telling you. So on the left hand side, what you have is the probability of A winning the game, starting with an initial capital of I, how that is related with the probabilities of A starting with a capital of I plus 1 and I minus 1. And how we argued was that first of all we made this connection that this gambler's ruin problem is exactly same as the problem of a random walker who starts with the position x equal to I, and you are asking the question, what is the probability that this random walker which hops to the right with probability q, what is the probability that this guy reaches I equal to n? When it reaches I equal to n, that means A basically wins the game. That means he gets all the capital from the B, and then the game finishes. So you are asking the question, what is the probability of A winning the game in this language of random walker? We also said that there are two boundary conditions that you have to remember. That means when P of A, I mean all the while I am referring to one, if P of A starts with an initial capital of 0, the probability of A winning the game is simply 0, because the game just doesn't, I mean if he's starting with initial capital of A equal to 0, that means he has no money, he can't bet, he just loses the game. That means B has all the capital. This is one of the boundary conditions. The other boundary condition is if I is equal to n, that means if A has all the capital and B does not have any capital, then the probability of A winning the game is 1. So these are the two boundary conditions, and then we came to this recursion relation, which is essentially telling you, one second, I'll just admit all. Okay, so what it is telling you is that the probability of A being at particular I can look at a one-step process. So suppose you are at A is at a particular site I, then the probability with which if it takes one step, then it takes with a step with a probability P, it can hop to this neighboring site at I plus 1. And if it is, so then it is exactly the, so if it has already hopped to the site I plus 1, then you are asking the question, what is the probability of A winning the, so if A is sitting here, the probability of A winning the game is P at I plus 1. And the probability of hopping to that side is P, so that gives the first term. The other possibility is if it has taken a step to the left, I mean if it had gone here, that means it has gone to this position of I minus 1, and that event happens with the probability Q. Then it is exactly the same problem. You are asking the question that this probability has to be either if it has taken one step to the right and then it is multiplied by whatever is the probability at I plus 1 plus Q times whatever is the probability of P at I minus 1. So this is the recursion relation which is satisfied, and remember that these two are the boundary conditions. So if you recognize, you have all seen differential equations in different contexts, I mean all this way. This has the, in terms of, so think of I as a variable. Think of I as an x, as x. So then, just like you have differential equation which involves full derivatives or partial derivatives for continuous variables. So there you treat the variable itself for a differential equation. The variables, underlying variables themselves are continuous. Here you notice how we have defined the problem. The sides I can only take discrete values, right? They can only take integer values. That means the I can be, how we have defined the problem, I can be 20, 21, etc. Any number, basically any integer between 0 and capital N. So if capital N is 100, then. So I takes discrete values. So this relation, which is relating, I plus 1 with I minus 1, is a difference equation. In that sense, you have encountered it even in your computer 1 course whenever you are writing down the recursion relations. So those are basically this kind of difference equation instead of discrete equations. Now question is, just like for differential equations, we want to find out what is the solution of such differential equations. There is a whole gamut of techniques of even handling this kind of differential equation, and you want to find out what are the possible solutions for this particular difference equations, and these are the corresponding boundary conditions for this problem. So I will not go into the general theory of difference equation, but just like what you remember from your MMP1 courses, that when you try to solve in general a differential equation, some of the methods that were developed one was series solution method, right? You try a series solution, you substituted into the underlying equations, and from that series solutions, you basically, you encountered this as an example for Hermite polynomials or, for Bessel functions, all these examples. So in similar spirit, what you can do is, you can try a trial solution. So one of the trial solutions that I would try for this particular case, which will satisfy, remember, it has to satisfy this particular difference equation. Let me call it equation 1, and let me call this boundary conditions as 2. So you substitute trial solution, and what is your trial solution? So you take a trial solution P of I, which let's say goes as z to the power of I. Substitute this in 1. So substitute this trial solution, substitute, let me call this 3, substitute 3 in 1. Basically our task is to find out what is z, but we are assuming some form that the solution of Pi has this particular form, and I substitute in this equation 1. And if you substitute in equation 1, then what you can immediately see is, let me, one second. Yeah, so I want you to see this connection, that once you have substituted in this original equation this particular form of P of I, then what would you have? Left hand side, if you substitute it in the left hand side, this will give you z to the power of I. Then you would have here P of z to the power of I plus 1, and then you have q of z to the power of I minus 1. Okay? You can easily see that if you cancellation, this particular equation, this can just simply be rewritten as p z square minus z right? I mean, all the different powers of z you can cancel off, and then you are basically left with this equation on simplification. You can immediately, of course, see that this is a quadratic equation in z. So there would be, you know, the way to find out the roots. In fact, what would really help you is, so you can test this. So q is not something independent. Q is actually 1 minus p. So this equation, because remember, I mean, p plus q always has to be equal to 1. I mean, there are only two possibilities. It hops at any I side, it hops to the right with probability p and to the left with probability q, and together they have to add up to 1 because of conservation of probability. So basically, this equation is also equivalent to this equation. You can solve this equation, so I will not go through the nitty-gritty details of solving quadratic equation. You know very well how to solve it. What you will get is, let me write this original. So the solutions of this equation . So let me call it equation 4. So this is equation 4. So solutions of equation 4 are, so there are two solutions. Either z is equal to 1, or the other solution, and it is a quadratic equation. In general, there would be two solutions. The other equations is given. Okay. Yeah, I mean, otherwise it is, in terms of algebra, it is pretty straightforward. What you did was you started with this recursion relation. You assumed a trial solution of the form z to the power of I. You substituted it back into the iteration equation or the recursion relation, and you, after simplification, you got a quadratic equation in z whose solutions are, so you can easily check, convince yourself that the two solutions of this quadratic equation is 1 and p by q. Okay. Remember, your p of I has this form. We had assumed was that it has this trial solution which is of the form of z to the power of I. So the next step is, so these are the two possible solutions. So in general, the form of the general solutions for this particular difference equation would be the following. So question is, how do you determine which of the solution does it take, or is it some linear combination of this solution? And the answer is that the general solution for this problem of, that means this general solution for p of I is some linear combination of these two different solutions that you have obtained. So that is the main crux of the matter. So that means it has to have the form following form. So general solution of Pi of A. So this would be of the form. Let's call it, we want to have two constants. So let me just call it C. Remember, the two solutions are 1 and P by Q. So it has to be of the form C into 1. I mean, just to emphasize that because it is one of the solutions, you write C into 1 plus D into P. Okay. So let me call this equation 5. Now our task is to determine what is it that fixes my C and D. Because once you know, so I mean, you still have two indeterminate things, which is this constants C and D. So their status, just like in any differential equation, you have this integration constants, right? So in differential equations, how do you fix those constants? Do you remember? I mean, can anyone tell me how do you fix this integration constant?
Sir, we could have conditions given in the problem accordingly.
Yeah. Meaning, what I mean to say is that if you have a differential equation, the generic, what do? You basically do a boundary value problem, right? I mean, we have been doing even in context of showing solutions of differential equations. You have a differential equation and then you have to have a boundary condition. How many boundary conditions you need, that will depend on the order of the equation. If it is a first order equation, you need only one condition. But let's say you have a second order differential equation, then you have these two different kind of boundary condition where you have either the initial value problem where you specify the value of the function at one of the boundary and the slope at the same boundary, or you specify the value of the function at the two boundaries, right? That is the general way in which you would proceed. So you would use that information of the boundary to finally find out. So that boundary condition is going to basically fix your integration constants. Similarly, even for the differential equation, the boundary condition which you have to take care of and which will actually going to fix what is going to be your this integration constant or the unknown for the time being C and D are these two boundary conditions which you have to use. Okay, so that means it is rather straightforward. Now the way to proceed is familiar. What you will do? So now if you want to substitute it, that means if it is at I equal to 1. Oh, sorry, I made a mistake. So I should put here to the power of I. See, I had assumed a solution of the form z to the power of I. 1 to the power of I did not write because 1 to the power of I is just simply 1. The general solution is of the form of, that means the general solution is of the form of C plus D multiplied by E by Q raised to the power of I. Okay. So now you just substitute. So if I look at the first boundary condition, that means at I equal to 0, this would simply be C. If I put I equal to 0, that means C plus D. And the boundary condition is telling me that C plus D is equal to 0. Look here. This fixes the boundary condition. This is one of the boundary condition that is imposed. That means if A had started with an initial capital of 0, then the probability of A winning the game is 0. So I have just simply used that information, and that is leading to this statement that C plus D have to equal to 0. And the other boundary condition is, that means if I look at I equal to N, then again left hand side I have C and then I have D, and here P by Q raised to the power of capital N, that has to be equal to, okay. So these two, so I can rename this if you like, this, let's say equation 6. And you know, you can immediately see this would just imply C equal to minus D. You just substitute it. C into 1 minus and this would immediately fix the value of C, which would be given by 1 minus P by Q to the power of N, and D is simply minus of C, so D is just minus 1 minus P by Q. Right? So your whole solution, which you have written down, now that you know the explicit expression of C and D in terms of P and Q, you can now, now that you have determined all these two constants C and D, you basically, that means, know the exact solution of this differential equation. That means you know the answer, what is the probability of I, of A winning the game starting with an initial capital of I. Okay, so basically that means you substitute this. 1 second. Any questions until here? Are the steps clear or some step is not clear? I mean, you can of course have a look at your notes just to whatever we have discussed. So basically, what we are saying is that, so I sort of skip the intermediate step now that you know C and D. Basically, so I'll just write substituting, I'll just write the final expression. You can do the simplification, algebra simplification. Substituting the value of C and D, P of I, that means the probability of A winning the game starting with I. This is simply, I'll just write this. Yeah, I can just rearrange. So I've just nicely rearranged the thing in this particular form. Okay. See, we would come to the analysis of this expression. But before we do that, one thing you notice is that, at as long as Q is not equal to P, this is indeed the solution. Whatever I have, I mean, after you have substituted C and D and all these things, you get this solution. But when Q is equal to P, that means both of them are half, because remember P plus Q is always equal to 1. In that case, even if you look at this expression, you see that, this expression, if you substitute this is, P is equal to Q, then you immediately have this 0 by 0, right? So then the way to proceed is like you have, you use the L'Hopital's rule, or what is the L'Hopital's rule? That means you call this variable x, and this is something, I think, whatever your high school calculus, what you learned is, so this, that means you have to, the limit x tends to 1, and here you have 1 minus x to the power of I, 1 minus x to the power of n, and you can easily see, of course, this is 0 by 0 form. And what L'Hopital's rule tells you is that in such cases where it is 0 by 0 form, all you have to do is just differentiate the numerator and differentiate the denominator with respect to x, and then evaluate the limit. Right? That is the well-known L'Hopital's rule. And if you do that, so if you differentiate the numerator, then what you would get is, of course, minus I x to the power of I minus 1, and then in the denominator you would have minus n x to the power of n minus 1, and then you have to take this limit x tends to 1. And if you do that, so for the case for P equal to Q equal to half, your answer is P of I is equal to I by U. Is this derivation clear, or any of you have a doubt on how we have proceeded? Yes or no? Is it clear? So if you are not responding, I assume that it's clear to everyone. But I mean, if anything is unclear, let me know, because all of this would be part of whatever you are expected to know. So this is the derivation. But let us now try to analyze the result. So let us begin with the analysis of the result when P is equal to Q. What does it imply? So when P is equal to Q, what we just derived now is, when P equal to Q equal to half, then what we just derived is that the probability of A winning the game is equal to I by n. Okay. This is of course a linear function of I, that is number one. But assume, so you should try to understand what is the limiting behavior of this function when n is very large. What does n being very large, this limit mean? When n is much larger than I, P of I, because it is a fraction, I mean, more and more n is larger than I, this will actually tend to 0 as n goes to infinity limit. Nonetheless, I mean, the main important point is if like n is like, let's say n is 100 and I is 10, then the probability of A winning the game is simply 10 by 100, that means 1 by 10. A has less probability. If the, that means if the starting capital of the total starting capital of the other player, the player who has larger capital, has much greater chance of winning the game, although apparently at each move the probability of the small games or the individual sequences, although they are equal. See, when P and Q, that means whenever A and B are playing the game, each time they are sort of tossing an unbiased coin, and you might get the impression that the game is fair because everyone has both have probability of half. But the fact that one guy has much less capital than the other, that means in this case, suppose n is much larger than I, that would mean B has much more initial capital, then the probability of the person who has larger capital is much higher than the other guy, and conversely, I mean, the one who has smaller capital has much lower probability, and this goes as I by n. So even though the coin tossing is fair, let's say if n is equal to 100, that means B has 90 rupees, and let's say A has an initial capital of 10, then the probability that A is going to win the game is just 1 by 10, whereas the probability of B winning the game is 9 by 10. So this is as far as the behavior of this gambler's ruin, and this also brings us to this situation that you imagine that why the name is called gambler's ruin is because if some small person with small amount of capital, typically when you go to a casino or any such gambling place, especially casino, so the casino has a lot of capital, so the value of n is typically much larger than a typical player, unless someone is a multimillionaire or someone, that's a different, but otherwise that number that the starting capital that you have and you play the game with is much smaller than the casino. So even in fact, typically the games that one plays in the casino, the odds of you winning the game or this mini games is not actually half. It would typically, the casino will always have a game where your probability of winning the game is less than half. But let's say even in the best case scenario where they actually give you the odds of equal probability of winning, your actual probability of the winning the game is much lower. I mean, if your capital is, let's say, 100 rupees and the casino has 10,000 rupees, then you can easily see that your chances of winning all the cash is it's in fact negligibly small as compared to someone who has much larger capital. So that is the most important lesson one actually learns from this problem. This, of course, so let me also briefly also look at the other case. What happens for the case where Q and P are not equal? So let us analyze what is this limiting behavior. So we are interested, basically what I am interested in is what happens in the limit when n tends to infinity or n is much larger than I. When n tends to infinity. So we have analyzed when Q is not equal. What happens if P, if this is less than Q, that is one case, and again n going to infinity limit, and the other limit is where P is greater than Q. If you actually analyze the case that, if Q, what did I do? Yeah. So if Q by P, if this is, that means in this case, that means in P is much larger than Q. And then in the n going to infinity limit, this expression would simply be almost 10 to this expression 1 minus Q by P. Okay. So when your probability of the A winning is more than Q, then the limiting expression of n going to infinity limit gives you a limiting value of P of I, which goes as, I mean, this you can easily see, because if Q and P is less than 1, this raised to n and n going to infinity, this will just simply go to 0, and what you are left with is whatever you see in the denominator, which is 1 minus Q by P to the power of I. That is the answer. What I leave as an exercise is that the other case, when P is less than Q, and if you are interested in studying the behavior, what happens when n tends to infinity, you find out. I mean, you have to be careful. You can, what you can do is you define a new variable. So you just say Q by P is equal to 1 by x, and then look, basically that means you look at this other limit. And what you would find is that in this case, that when P is less than Q, this probability P of I, this would tend to 0. Okay, so there are these three results. So for the case when P and Q are exactly equal to half, then you have a result that P of I, of course, goes as I by n. Even for this case, if you actually take the limit of n going to infinity, the probability of A winning the game, again, in fact, even for this case, it would tend to 0. What the cases where P is less than Q, again, n going to infinity limit, the result is that it has a probability which is vanishingly small. And then you have the third case where the P is greater than 0, then this is the expression for the probability of A winning the game, starting with an initial capital of I, which does not go to 0, and which is this. Okay, so this is as far as the problem goes, but this has, interesting implications. So what it is, first of all, like I told you, from the perspective of a gambler who is going to a casino, that means if you are someone who is having small capital and you even play apparently this fair game where your probabilities of these mini games is half, then also in the net sum, the probability that you lose all your money is extremely high if you are playing with someone whose starting capital is much higher than yours. That is the typical scenario in a casino where an individual gambler. So it might happen then that in one particular run, all these results are in an average what happens. So it might happen that one particular game you win. But on an average, if you look at the statistics, the odds of you winning the game is extremely small. Basically, it is dependent on how much the total capital of that casino is. This problem in some sense is also very interesting for the people who are doing economics or even the ideology of economics. At least some of you might be aware that when people talk about free market economics, that markets are the best forces which determine competition or free market. Everyone has equal chances of winning, so everyone can make it big, and everyone is equally likely to become rich or whatever. Rags to riches story that you keep on hearing. And what this gamblers rule problem actually tells you that all that thing is complete nonsense. It is just a propaganda game where where there are a lot of big players are involved. So in any kind of economics, whether it is you consider between small nations or big nations with less capital and more capital, or you look at even a simple aspect of where someone invests in a share of some company. So there also it is basically gambling, right? Someone you are whoever is the gambler, in this case the investor, they put in some capital. Now the chances of an investor with small capital, they making money is much smaller, and in fact their chances of losing the money is much higher especially if they are playing this game with someone who has much larger capital. That means if you're playing this game with an Ambani or an Adani, obviously your chances are close to zero. So there's no rags to riches story for that case, and if someone tells you that, you should show them this problem or calculation of gambler's win. So that was one comment I wanted to make in context of this gambler's ruin problem. Let us now come to how you are going to implement this problem by using Monte Carlo method. Before that, if you have any questions regarding this, you can ask and clarify. Otherwise, I'll go to the aspect of how, what I have derived here is the analytical form of the solution of the gambler's ruin problem. And in fact, what you should do is you should actually analyze the behavior, that if you change I, what happens if you take a finite n, what is the behavior, all these limiting properties I told you. But in general, you have the full form of the distributions. You can ask the following questions. But suppose the use of the power of Monte Carlo method, because we started this discussion of how you are going to use Monte Carlo method for finding out the different aspects. So here, how you can actually do the Monte Carlo simulation is pretty much straightforward. So I'll outline that. And in fact, this is the problem that you would have to do in your assignment. To use this Monte Carlo method to actually simulate this problem of gambler's ruin. And so the steps are the following. So steps Monte Carlo simulation of gambler's ruin. First step. So, like I told you, how you should imagine this problem is that means you are starting as a random walker at some I, and you have a probability of P of hopping to the neighboring site at I plus 1 and Q of hopping to the neighboring site at I minus 1. So what are the inputs for this problem? So the inputs that you have to provide are, of course, you have to specify what your initial I of your, in this problem is. That means your initial position for the random walker, or in the language of gambler's ruin, your initial capital. That is some integer number that you have to specify. You have to specify the total capital N. And in the language of random walker, that means the right end of the 1D random walker, whatever where it is defined, right end of this discrete lattice. So that means you have to specify I, you have to specify N, and you have to specify what is the probability of A hopping to the right. By default, of course, once you specify P, you are specifying Q because Q is just 1 minus P. So these are the three inputs that you have to provide. Now, how do you actually go about simulating the Monte Carlo simulation of this? So let me, before I actually write it down, what you need to do. So let me just go through in words and then I can write it down. So first of all, let's say you want to simulate one run. That means what you actually want the computer to do using the property. The main idea is you want to use the property of uniform random number generator, which we discussed in last couple of classes, to simulate somehow this probabilities. What is every time happening? You are basically tossing a coin, biased coin, let's say, with probability P and Q. So that means you have to somehow simulate first of all these probabilities P and Q, and you have to keep on playing this game. So you specify, that means you have some initial position. Let's to give an example, let's say your I is equal to initially 20 and your P is, let's say, 2 by 3 and your capital N, let's say that means the total capital share between A and B, let's say that is 50. So you start, that means your initial value of I is 20. Then remember the probability of hopping to the right in P we just mentioned is 2 by 3. So what we will do, we'll call a random number, uniform random number. If that and the computer uniform random number is a random number which is lying between 0 and 1 and with equal distribution of these numbers. Now when you call this random variable xi, uniform random number variable xi, if it is less than p, that means in this case if I have chosen p to be 2 by 3, then if that random number called is less than 2 by 3, then you update the position of I from its initial position, that means you started from this position of 20, you make it 21. Again you call a random number. Again you do the same exercise. If the number you find is less than 2 by 3, then you update the position of this A from 21 to 22. If you find, then and you keep on doing this process. If the random number that you call, if it is more than 2 by 3, that means that is like A losing a mini game. In that case, this 22 will become 21. So you have to keep on doing this. That means this keep on you will need a do loop which will keep on this calling this uniform random number generator, and every time you call the random number generator, and then you will have an if statement which will check whether it is greater than p, if the random number is greater than p or less than p. And depending on that, you will keep on updating the position x from whatever starting position, and you keep on continuing doing it. See, remember, the game finishes whenever either the random walker reaches x equal to 0 or x equal to n. So if you started with 20, you should keep on doing this process until x has either reached, I mean, there are only two possibilities how the game can finish. Either x has reached n equal to 50, or it has reached x equal to 0. Any of this, I mean, because it's a random number, sometimes you will get n equal to 0, sometimes you will get, whenever, let's say, first time you play this game, then you have to keep on doing this do loop until any of this. Let's say for the first time you do this Monte Carlo simulation, you get the result that the game finishes at x equal to 0. You should have a counter which will keep track of how many times you have a particular realization which is achieved. That means first time you do this game using this uniform random number generator, let's say you get this result x equal to 0. Second time you play the game, let's say again you get this result x equal to 0. Third time you play the game, you might get the result that the game has ended with x equal to n. What are finally the probability of A winning the game starting with I is nothing but you have to count. So if you do this large number of times, so just think of the ideas that we have developed in statistical mechanics. That means you have to consider an ensemble of systems. That means you have to keep on performing these experiments in computer very large number of times. By large, I mean okay, at least 1,000, typically like 10,000 times. So that means 10 out of 10,000 times, if you start with the same initial condition I equal to 20 and with the same p, you will sometimes out of this 10,000 times, maybe 2,550 times, you find that A has reached x equal to 0, and rest 2,000 whatever 450 times it has reached I equal to n. The probability of A winning the game is simply the time it has reached, that means it has won the game is when it has reached. So you take the total, you just divide the total number of frequencies or total number of times it has reached x equal to n, divided by the total number of attempts. That means if you are doing for 10,000 times, then you divide it by that. Whatever is this ratio is nothing but basically you have simulated or obtained the value of the probability of A winning the game. How accurate is your result, like I mentioned, would depend on how many times you perform this experiment. That means if you have done only 100 times and you calculate this ratio, that result would be less accurate as compared to if you have done it 10,000 times and found out this ratio. So the more number of times you do, the actual the probability that you obtain from your Monte Carlo simulation method would tend towards, so the error that it will be making, and when comparing, see, we have already found out the exact result, that exact analytical result. So the difference of that you can find out, so it will keep on approaching the exact analytical result as you keep on doing more number of times this particular simulations. So anyways, maybe since we are running out of time, so this is sort of the outline of how you do the Monte Carlo simulation process for the system. So tomorrow when we meet, we would spend more times in details of how you actually do the Monte Carlo simulation for this method. You can actually ask even other questions. So for instance, you can ask this question that here we had asked this question that what is the probability of A winning the game? But you can ask the question, what is the probability distribution? So you can imagine that every time you do the game, there would be different durations for which this game is being played. So what is the underlying probability distribution of a duration of a particular game? And again, you can use this Monte Carlo method to actually simulate or generate, every time you will have some duration, and you can keep track and draw a histogram and actually find out the distribution function for the duration of the game, just like you are able to generate the probability of A winning the game or correspondingly B winning the game. So we will dwell in more details tomorrow. And one more thing is that I want to take, because Wednesday I might have a problem the original time. So I will take one extra lecture. So you will of course have the usual lecture at 10 o'clock, 10:10 tomorrow. But I want to have another extra lecture at 4 o'clock. Do you, any of you have any other lecture at 4 o'clock tomorrow in the afternoon? Yes or no?
Excuse me.
Yes.
Sir, we have lecture from 3 p.m. to 4 p.m. So can we shift it to 4:15 p.m.?
Oh, good. Okay, fine. So that I can do. So we can then have a lecture from 4. So let us make it at yeah. So 4:15 you can log in. I can start. So by 4:15 if you log in, we'll start teaching by 4:20. Fine. So we will have the usual lecture. So again, once again, I repeat. We would have the usual lecture at 10 or 10:20 like today, the normal lecture tomorrow. And then we would have one lecture at 4:20. You can log in from 4:15. So from 4:20 I will start tomorrow.
Sir,
Yes.
sir, we have a quantum information lecture at 4:30 to 6.
You have a quantum information lecture?
Yes,
Who is
at
taking?
at 4:30 to 6 p.m.
Online?
Yes.
Okay, so then the other possibility is, so 3 to 4 you have this lecture of ED?
Sir, astrophysics.
3 to 4? So
Yes.
then let me do one thing. We can then have the lecture from 2 to 3.
Yes.
Is that okay with everyone? Then it does not clash with any other lectures.
Okay.
Fine? Yeah, so then please also inform others that we will of course have the usual lecture tomorrow at 10:10, and we would have one more extra lecture at 2 o'clock. So you can log in at 2 o'clock. By 2:10 we would start. So latest 10. I will start my lecture by 2:10 for sure. You can start logging from 2 o'clock. And yeah, so coming back, if you have any doubts about whatever I taught today, you can of course go ahead. If you do not have doubts, I'll terminate my lecture today. Stop here. Fine. So if there are no doubts, then we meet tomorrow at 10:10.